when we did a review on quantum numbers, we talked a little bit about spin-orbit coupling then. If you recall, we had our Russell-Saunders scheme, which is the spin multiplicity with our orbital angular momentum. And then we had we mentioned that orbital angular momentum, so the magnetic dipole of the electron traveling around in its orbital can couple to the spin, this magnetic dipole caused by the spin. So the electron has a spin and it's moving around. And so these two values, the orbital angular momentum and the spin angular momentum, can couple to then form J, which is the total angular momentum. And if you recall, this is typically, so J can have values going from the absolute value of L minus S, that plus 1, dot, 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 all the way to L plus S. OK. So typically, for 3D with a certain number of electrons, metals or ions, molecules, usually this total angular momentum, this spin-orbit coupling parameter, like how much these are split, these different J values, spin-orbit coupling small relative to electron-electron repulsion, or our ligand field splitting if we have it in a molecule. So spin-orbit coupling still happens. It's going to be smaller in magnitude. For maybe 4D N, so your lower transition metals, second and third row, and also any F element, your lanthanides or your actinides, spin-orbit coupling can have a much bigger effect. So when we have more protons in your nucleus, things are moving around faster, maybe just bigger orbitals, this coupling could be more important. So these are our relative terms. So often for the 3D elements, we can ignore spin-orbit coupling in spectroscopy. It does have some effects on our appearance of our spectra, but often it can be ignored. In the 4D, 5D F elements, it cannot be ignored because it's so big. In fact, in some scenarios, you might even start off with spin-orbit coupling as a splitting and then do your perturbations of electron-electron repulsion or the ligand field. It's that much bigger. OK. What else did I want to say? OK, so if you recall for our atomic terms, so just as one example, if we use, this was our Russell-Saunders scheme for atomic term symbols. So as one example, if you remember, if we did a D2 free ion configuration, so a free ion, no ligands, one of those free ion terms was the triplet p term. So in this case, so for a triplet state, S equals 1. For a p term, L equals 1. So this means that J must therefore equal 1 minus 1 is 0, 1, or 2. So that because L plus S is 2, so 0 and then plus 1 plus 2. So therefore, our free ion term, so remember this is from electron-electron repulsion of our D2 configuration, and that there were other terms as well from electron-electron repulsion. So this, by spin-orbit coupling, is then split off into 3 different levels. Let me just draw this relative here. And then this was J equals 0, J equals 1, J equals 2. If you remember, this ordering was from Hund's rules, and this ordering is 0 to 2 because the d orbitals are less than half filled. And then so these are split to different energies. So and then we have what's called kind of like the spin-orbit coupling parameter. So there's an eta term, or is it a zeta? Anyway, it looks like this. But then multiplied out by L times S, this splitting is usually referred to as a lambda. So this difference is lambda. This difference is 2 lambda. And so how much spin-orbit coupling there is between our orbital angular momentum and our spin angular momentum dictates how big lambda is. Let's say one thing to mention is for a 3D metal, lambda is usually around 100 wave number. And then, of course, remember our delta O's were on like from ligand field. If you remember these were on the order of like 10,000 wave number. So much bigger. So you can see for a 3D metal, the spin orbit coupling, how much that's split is going to be much smaller compared to our ligand field splitting. So this is just to sort of calibrate you. OK, let's see. So the effects of this are, let me see. So effects on spectroscopy. One thing is, spin orbit coupling is the primary mechanism for observing spin forbidden transitions. So for example, if our ground state was like a triplet A2G, for example, and spin allowed transitions have to go to a triplet excited state, so a singlet excited state is spin forbidden. But if there's spin orbit coupling, then remember, S will no longer be a good quantum number. So we have to look at coupling between S and L for the J. And then because of that, the spin forbidden no longer really applies. So basically, the bigger your spin orbit coupling is, spin orbit coupling up, so like a big lambda. So if that's the case, then you have more intense spin forbidden bands relative to our spin allowed bands. So we mentioned in class from our selection rules that the spin allowed transitions are all going to be much, much more intense than the spin forbidden ones. If we have high spin orbit coupling, that will no longer, that might change, so you might get closer in intensity between your spin forbidden bands and your spin allowed bands. So if you compare, like if you go down the transition metal groups, we might see more intense spin forbidden bands because, as we said up here, the 4D, 5D elements have higher spin orbit coupling than the 3D elements. So that's one primary mechanism. OK. Let's see. Effect number 2 is this results because we have kind of like the splitting of certain states into the spin orbit coupling states, then how much these are split determines the width of your band. So your absorption band will have a certain width, and then that's going to be related to your spin orbit coupling, right? So the bigger your lambda is, then we have our ground state might be split into many, like a wide band, and then so all these energies can then excite up, so then you're going to have a large bandwidth. So it's, again, related to lambda, you'll have broader bands. In some cases, because we're split, then you also might see fine structure within the band. Fine structure, because right, our ground state could be split, or our excited state could be split by spin orbit coupling. So we have multiple states, we could have multiple transitions. And then so rather than seeing one band from a ground state to excited state, if our ground state or excited states are split, then we might actually end up seeing something like, right? So these are going to be the splittings from our spin orbit coupling, and then our band shape will end up looking like this. So this is a scenario where here we have something like, if this is maybe lambda, or our spin orbit coupling parameter, how much these are split is going to be related, this is going to be smaller than our overall, the energy of where your transition actually is, right? So this is the energy of going from the ground state to the excited state. We'll do an example of this in class. I will say often, so this phi structure is often too broad to be observed for 3D. But there are specific cases that we'll talk about where you can see it. So not observed. So often, instead of seeing the fine structure, we'll just see a broadened band. So instead of seeing this, we might actually just see kind of like it's just overall broadened like that. So it's hard to make out the actual fine structure in some cases. Okay, let me quickly erase, and we'll do just a kind of example of how spin-orbit coupling can be ends up with a splitting in an actual electron configuration. Okay, so spin-orbit coupling has to happen when you have different L terms and different S terms, different L values and different S values for your quantum numbers. So often you have a degenerate state in the octahedral symmetry, and then that results in splitting. So one kind of ingenious way that people, so there's a lot of math that you could do, but we'll just do kind of one abbreviation, which was that someone realized that in the octahedral geometry, T2G has three degenerate orbitals, so this kind of looks like p orbitals. We have 3 degenerate p orbitals. So if we want to do an example, so let's suppose we have D2 in octahedral. We know that the ground state configuration is going to be W occupied T2G. So this will look like a P2 atom. So this is molecular with ligand field, and then this is free atom. Okay, so for a P2 electron configuration for a free ion, I'll leave it up to you to show that this P2 configuration will result in 3 terms. And so you're going to have your ground state, which is triplet P, and then we have singlet D, and then singlet S. So these are our free ion terms for P2. And then if you look at how this spin-orbit coupling should go, the only option here is for this one to split. So this one will split off into J equals 0, J equals 1, J equals 2, just like we just showed in that previous board that I just erased. So because T2G2 looks like 2 W-occupied p orbitals, we can take T2G2, and then it has to split. We'll first do our electron-electron repulsion, and it's got to look really similar, because this is also electron-electron repulsion, right? This is electron-electron repulsion. So to split that, we're going to, we did this already in class, so just suffice it to say, this ground state was triplet T. I need to make sure. T2G, or T1G, T1G. Then we had our singlet T2G. And then we had up here was singlet A2G. I might have gotten labels wrong. If so, I'll comment in the comments. I just can't read my handwriting for the subscripts. So these two will match. Oh, right, this was singlet EG. Sorry, there's 2 of them. There, so these 2 states. So these states match the singlet D, right, which is 5-fold degenerate. There's 2, there's 3, singly degenerate, singly degenerate. And then so this is the triply degenerate P term and the triply degenerate T term. And then so just like this one must split off into J equals 0, J equals 1, J equals 2, once we apply spin-orbit coupling, this one can also split off into J equals 0, J equals 1, J equals 2. And then so overall, this splitting determines our bandwidth, because this is the ground state for all the D2 octahedral. So if this is split, we're going to have kind of like a wide range of starting energies that we can go up to our excited state. and then so we're going to have the larger bandwidth. So we'll do some more examples in class.